I attended two presentations today at Stanford. They're part of a series of lectures by professors for first-year PhD students, and the idea is to give them ideas of what kind of research they could be doing or what kind of ideas they should be working on. So let me start with Azalia Mirhoseini. Azalia Mirhoseini, she works at Stanford in the so-called scaling intelligence lab. And the idea here is really to build systems that can scale intelligence and that scale systems with intelligence. So she's attacking the problem from both ways. Very interesting. Her presentation's a bit boring, but the content of her work is very interesting. Her work on automated verification and automated unit testing, because think about it, like, for example, if you prompt a large language model to give you, to write a piece of code to do something, you could have an automated unit test going through, let's say, various examples of the same code and then give you the best solution. So what she's working on is actually what OpenAI just recently has released, which is the the O1 model, I believe, a model that is more interested in delivering better inference, so spending some more time on inference and having better inference, and not just this one shot, okay, I have memorized everything and I give you the most likely scenario in the one answer, but I spend some time researching the amount of possible answers and then give you the best answers. This is also akin to what Sergey Levine was talking about about 6 months ago in one of the keynotes. I'll put the link in the show notes, where he compared unsupervised classification and reinforcement learning. So you have this unsupervised learning, which is able to classify all kinds of possible scenarios, and then reinforcement learning being the optimal path towards a particular solution. So what Azalia, I'm sorry, I might be butchering her name, but what Azalia is really working on is what I've been saying for a long time, which is that what we're most interested in is tokens per dollar, actually even solutions per dollar. So she's working on that problem. The other presentation was about algorithmic fairness and algorithmic allocation problems. So this is a field that is very dear to my heart because it sort of tangentially, passes by economics. The idea is in the presentation, the professor, it wasn't actually Omer Reingold, it was one of his deputies. Omer wasn't available, but the same thing, same type of subject. What the person was talking about was, the idea was the following: like, you have, let's say, a certain amount of seats in a class that can be allocated to students, and how do you allocate that, right? So this is resource allocation, and there's a lot of interesting questions and problems that come with that. In particular, of course, the question of fairness. This is not even on podcast. It's November 23rd, 2024. This is Krendelko for today. The fund is up 4.9%. The market's up 30 basis points. For the year, we are up 19.5%. The market's up 19.6%, round forward by 10 basis points. Today, we had a large move in Tesla. We're approaching the Q3 numbers. And of course, we're approaching the robotaxi event. And I believe that there is positioning going into those two events. And that was the main driver. Let's talk about these presentations. So the year has started. The academic year 24-25 has started. Today was the first day, and I attended one of the really interesting classes here at Stanford. It's called Computer Science Lectures, and the idea is that you have a professor showing up for 40 minutes talking about what they do, and inspiring first-year PhD students to follow that path and get interested in some of the work that they do. This is, it's perfect for me because this is still part of my sabbatical, so I'm not interested in learning the nitty-gritty technicalities of every problem. I'm much more interested in the big picture analysis of what is out there, what are the problems, and then how can we apply this to our fund. For a reminder for first-time listeners or new listeners, the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. We run Orange Capital Partners, which is an opportunistic hedge fund. Opportunistic being we We have no, index attachment, or we're not sort of a relative performance type fund or anything like that. We simply we were just judged on how much money we make, or in technical terms, we're judged on alpha and not beta. Now, let's talk about what we're doing here and why we're doing this. So we've said several times on this podcast also that knowledge creation is really at the heart of our business. I mean, this is what we do. And, we're not scientists or novelists or anything like that, but we are in the knowledge creation business. And knowledge creation requires exploration. It requires trying to approach problems from an epistemological perspective. What that means in plain English just means that, look, there's no book written about how to do this. There's no perfect solution or anything like that. This is a creative job, and the way we do it is we are mostly interested in cutting edge science that is sort of spilling over into technology and then spilling over into entrepreneurship and business. This could happen at the startup level. This could happen at a Tesla level, or a Nvidia level, or at a mid-sized company level. We're not married to any particular size. We're also an opportunistic hedge fund when it comes to asset classes. We do, mainly equities because we see most value in equities, but we're also invested in Bitcoin. Not a lot, but there is some investment there. So we have certain asset allocation questions to also discuss sometimes. So today we're going to talk about really the heart of what we do, which is knowledge creation. And that is, in this case, we attend lectures at Stanford. Knowledge creation encompasses a broad field, reading books, going to conferences, talking to people, reading nonfiction, reading technical papers. So we're interested in all kinds of knowledge. And of course, this is a big field, and we have to optimize. And the way we optimize is, for example, we spend more time at an institution like Stanford or MIT or Berkeley, and maybe a bit less time at the Art Institute of Chicago. Not that the knowledge there is not important or anything like that, but for us, in terms of time management and resource allocation, this is just the best way to use our time. So this is a good segue into the first presentation. It is part of Omer Reingold's department, theoretical computer science, in particular algorithmic fairness. So this is really an interesting problem, very dear to my heart, because it does sort of tangentially crosses paths with economics, which is what I've been trained in undergrad. So the problem is, okay, how do you allocate, let's say, a limited amount of classes or class seats at a university? So there's 100 students want to take a class that only has 20 spots. And, the professor went through a couple of solutions. There's some mathematical stuff going on. But fundamentally, what we're aspiring to here is a pareto optimality, or a John Rawlsian fairness, or a Kantian categorical imperative. I think these concepts are all very similar. In principle, what it means is that we want to have an allocation such that we cannot change one thing, and we cannot improve one person without hurting anybody else, right? So if we have a system where we couldn't change one, we could improve, let's say we have 100 people, and I pick John, and I give John a little bit more, and nobody else is affected by this. If the system is such, then it's not Pareto optimal, or it's not fair. In other words, fair is if we are at the Pareto optimality of we can't do anything without hurting somebody else. Now, there's a little bit more than that on the constraint side. For example, there's a constraint also that the professor introduced, which is NV-free, right? And to me, that is kind of a rabbit hole that I think is very dangerous, because it's sort of a Gödelian incompleteness rabbit hole. If you say that I define fairness by NV-free, then you have to define NV, and then you have to define whatever you define NV with. And unfortunately, I think you're going down a rabbit hole here, which doesn't really have a satisfactory solution. So my point was, my idea here is that the best way to achieve fairness is not to have some algorithmic solution or anything like that in terms of a mathematical, like this bigger than that or this equal that. I think the best way that humans, we psychologically respond to fairness the best is if we're involved in the decision-making process. In other words, if we had, for example, some sort of proof of work where, let's say you have 20 spots which are available, 100 people want the spots, so you do, let's say you do a project, everybody has to do the project, and then the peers evaluate the 20 best. You can't evaluate yourself, but you can evaluate everybody else. So to me, that is the best path towards fairness, because it seems that humans, and this is now psychology, and this is why also this is so interesting, right? Because now you're in economics, you're in psychology, you're in comp sci, you're really tangentially passing through many, many fields, and I think particularly at Stanford, that's something that is very encouraged here. I think it's also the right path towards a solution. So you don't want to be caught up in a Gödelian incompleteness or a sort of Hofstadterian loop where you're defining this with that and then that with this, and then at the end you end up, let's say, defining fairness with envy and envy with fairness, and you could say that fairness is if something is envy-free and envy is if something is unfair. I mean, you know what I'm saying? Like, we're going into a loop here, so we don't want that. But I think if we give people a chance to be part of the decision-making process, so if we don't make it coercive by an authority, where the University of Stanford, the admissions process, or the allocation, the class allocation ministry of class allocation, or something like that, then I think it comes across as more fair. So this would be the first presentation. The second presentation I attended today is by a lady called, and I hope Azalia Mirhoseini. Azalia Mirhoseini. She's a professor here at Stanford, and she talks about scaling intelligence. In my opinion, also a very, very interesting field. I saw her at the MLSys conference about maybe early this year, maybe something like that. I'll put the link in the show notes. I think I spoke about her back then. So what she's doing is really sort of she's at the cutting edge of computer science, and because it is all about scaling intelligence, right? So we figured out a way to extract intelligence from data. We've done it since ImageNet with Fei-Fei Li's ImageNet, and then supervised learning, and then we have unsupervised learning, and culminating in large language models or transformers culminating in large language models. Now we're at the frontiers of robotics, but all of these systems have one thing in common, which is they need to be able to scale. So we know that the more data we have and the more compute we throw at the system, the better our intelligence gets. So then the question, of course, is how can we increase the compute? How can we increase the data? What kind of data should we be using? And then also, how can we reduce the energy consumption? So what Azalia is really working on, in my opinion, is what I've been always saying is the holy grail is solutions per dollar. Okay, we want to get the most bang for the buck, and that can be done by having an efficient training method. And there's a couple of approaches out there. There is NVIDIA with its CUDA-based platform architecture, where the data center is the unit of compute. We have ASICs like Dojo or TPU, and then we have Cerberus and those guys who do on the chip level try to innovate. I think all these things, have legs. What the latest, which just came out of OpenAI, and what Azalia is also working on, is inference. And what that means is that, okay, you could have a massive amount of training, which is another word for compressed knowledge in a machine-readable vectorized way, and then extract the most likely answers to prompts. However, how about you also give yourself some time with the inference, or you train the machine to do better inference? This could happen through reinforcement learning, for example, and in particular also with automated unit tests. So not just that you have a preference allocation in a sense that you give the best answer to, let's say, what a human would prefer given the problem, but you're also doing automated unit tests, which is basically making sure that the solutions that you're offering are already pre-vetted. Kind of like, if you will, if a university is admitting students, a unit test would be something like an SAT or something like that. So you have some automated testing just before you even evaluate further actions. You want to make sure that the solution is valid. So that's what Azalia is working on. In my opinion, really very interesting, particularly the scaling inference and the scaling laws of inference. You could imagine something like one project she's working on, which is really fascinating, is large language monkeys, LLMs, large language monkeys. So what that is like, imagine you have a prompt, and then you, instead of just having one prompt and one solution, and then maybe have a human try a few prompts, you have parallel many millions and millions of prompts, slightly different with slightly different solutions, and then you use a sort of a reinforcement learning algorithm to navigate towards the best optimal solution for the given problem. And in my opinion, this is also reminiscent of Sergey Levine's talk that he gave about 6 months ago at the summer school. Yeah, it was a summer school, I believe in India somewhere, where he spoke about the combination of unsupervised learning and reinforcement learning, and how the unsupervised learning is sort of the classification part of the problem, and the reinforcement learning is the optimization part of the problem, and that we can kind of combine those two. Azalia is also working on optimized chip design, automated chip design, also very interesting. She has some other things like federated learning, but I think the large language monkeys and the automated unit test or automated validation, in my opinion, are the most interesting parts of her research. Thank you.